but I will get directly into the core. We will start by sticking to this difficult set of materials, the poroelastic materials. You got a very nice introduction. So I will not re-describe here what we have, but we will essentially take as test toy problems these vibro-acoustics. So acoustic cavity, you put some damping at the boundary of the cavity with those poroelastic materials. And how can we deal with this using reduced order models? You got exactly this type of problems highlighted by Olivier. You have some kind of a source in an acoustic cavity. And then at the boundary of that rigid cavity, in this case, you put a layer of absorbing material. This would be the poroelastic materials. And you can see here the formulation that I will use is one where instead of having the solid and total, you have the solid and the fluid phase displacement. This is the one dating back further in time than the one that was proposed by Olivier. That's the one that Bio actually introduced, that was enriched with the different parameters. And I will try to see, since this is very aligned with solid mechanics, to see, well, can we actually try to come up with a basis, a model basis that doesn't have the typical then nice properties outcome if we use that for the poroelastic materials, but that we can still use in a decent way there. So what is the problem then? The governing equations, we have the acoustic fluid governed by the Helmholtz equation, nothing strange here. When we have a look at the poroelastic materials, what you get to see here, we will have to deal with the constitutive relations for the solid and the fluid phase. You can see here this viscous term, viscous coupling, difference of displacement between the solid and fluid phase. Here some dissipation with the tilde is a complex valued quantity, and then omega frequency dependent quantity, but that's in factor of this difference of the displacements that we have here. So it's linked to velocity, it's sin I omega that we have here. And then you have here the inertial side of things, which is a bit expanded there in a way that we introduced explicitly this inertial coupling term, this rho density, rho A that you have there. And what I'm after here is to try to find a structure that would make these problems suited to calculate, to pose an eigenvalue problem where we could extract the modes and then project this whole problem on the set of coupled modes, which include both the solid and the fluid phase for this whole problem. And the problem, one of the problems, one of them you have it here. You can see a structure there where we have some kind of regularity there. This rho A for the solid fluid phase, and then these coupling terms that we have. The inertial terms, well, they appear somehow, and on both sides you have this difference of solid and fluid phase that appear there, and then you have something that is more specific to the solid phase, and here more specific to the fluid phase. All right, we could take this somehow as a mass matrix that is real valued, frequency independent. On the stiffness side, where we will discretize and have the finite element problem, we have to look at the constitutive relations. And if you have a look at the constitutive relations there, we would have coupled constitutive relations between the solid and the fluid phase. And you can see those constitutive matrices, those Hooke's equivalent tenses that we have there, they are frequency dependent, complex valued. Then we have to expand that a little bit to try to work this out, not as much in detail as what Olivier did, but if we have a look at expanding this, we have clearly a part that where we recognize some bits that are clearly associated with the structure. We have something there that is linked to somehow the coupling between the two phases, and then something that is more related to the second equation, directly associated with the compressibility of the fluid phase. And if we have a look further in details to those four parameters that we have here, which are complex and potentially frequency dependent, we can see that they all depend on this bulk modulus, complex frequency dependent. And then you detail further what this bulk modulus is equal to. You only need to remember complex frequency dependent. And conceptually, what we can do is to say, okay, but this term has the low frequency limit, P0, and then the complex frequency dependent part, the other part, such that we could somehow come down to a stiffness matrix that is separated into two parts, the low frequency part, limit, which is real valued frequency independent, and then the higher frequency part, which is complex valued and frequency dependent. You see here, there's two parts of the emerging stiffness matrix for the finite element problem, the low frequency limit there and higher frequency limit there. And what you can see in there is that then it depends on those submatrices that we have there, and they are all dependent on the same submatrix D which is only made of the longitudinal directions and the coupling between these compression extension terms. That indicates that there is some kind of regularity in the structure of those matrices, which maybe makes for a suitable enough eigenvalue problem where the modes could be helpful for the global problem that we have in the end. So let's move to the next step. What we detail now, this is a summary of the form of the governing equations, the PDEs that we have. And if we take this, then weak form, we move to the finite element or the discretized form. We essentially, if we now have a poroacoustic problem, you gather all the degrees of freedom, 6 of them, 3 for the solid displacement, 3 for the fluid displacement for the poroelastic medium under UP, 6 unknowns, and then the pressure degrees of freedom from the acoustic side. And you have a global problem of that form, a low frequency kind of stiffness matrix where you have a coupling between the acoustic fluid and the poroelastic material there. This mass matrix that we just took at the end as being, frequency independent in this case for the poroelastic materials. And we have here in the middle those two intermediate matrices, one associated with the viscous term and the other one with the higher frequency part of the stiffness matrix. And here comes the question, can we build an eigenvalue problem for the porous part built exclusively on the low frequency part of the stiffness porous matrix and the mass matrix that we have here? How suitable would that be for projecting also those other two submatrices on those modes? Because what we have in the end in this matrix, we actually carry, due to the structures, we have a linear combination of what is purely associated with the structure and the fluids, including the coupling to the structure. Those two are recombined, so somehow we carry the information that we have in there in this first part of the matrix, and it's in a similar way between the damping, the viscous damping matrix there and the inertial matrix that we have here. So this is what we will now look at, having a look at establishing an eigenvalue problem for this. And for that, I will just use a component mode synthesis approach as Olivier has introduced, where you can disregard, really, we will never take care of reducing in this presentation, at least the acoustic, purely acoustic part. We'll just, for practical reasons, we will separate it into interior acoustic degrees of freedom in the acoustic cavity, and then degrees of freedom at the boundary of the acoustic cavity, purely for the sake of using a model approach for the poroelastic degrees of freedom. So we will set up a basis just for the second part, which means that we use traditional component mode synthesis approach, where we keep the inner degrees of freedom for the acoustic part unchanged, the interface degrees of freedom unchanged, except that and then we use a model basis for reducing the porous degrees of freedom. And in order to link the interface to the inner degrees of freedom for the poroelastic domain, we will use attachment functions, the same that Olivier has been presenting, where essentially you impose a Dirichlet kind of boundary condition problem to the interface degrees of freedom, and you get the static response to that problem in the poroelastic layer. So now this model matrix, as I said, let's try to build it from those two low frequency stiffness and the mass matrix for the poroelastic medium, using 6 degrees of freedom in there, which will lead us to a set of porous modes. And then the attachment functions, as I said, they are the result of a Dirichlet type of problem, purely considering this part of the problem where we have the interface acoustic degrees of freedom and the poroelastic degrees of freedom there. If we project then the full poroacoustic problem on this CMS basis there, what we end up having is a problem in terms of interior acoustic degrees of freedom, the interface ones, and then modal coordinates for the poroelastic materials. And what happens for the modal materials? Well, we have built the modes based on the low frequency stiffness matrix and the mass matrix. So those ones are naturally diagonal. We expect those by construction to be just diagonal terms in these submatrices. The question, of course, is there is no reason a priori to have diagonal submatrices when it comes to having projected the viscous part and the viscous matrix part and the higher frequency stiffness part on those same modes. That we will come and check later. We know that there's a structure that is fairly parallel, so you will see alignment of subspaces in a second part. I think when Sebastian will be talking about this, here we can anticipate that maybe there are part of those that are fairly well, or the two subspaces, the subspaces are fairly well aligned to those that will be built on those matrices instead, which could lead to subdiagonal matrices for those as well. This is something we will come back to a bit later. What happens? Let's test this basis there. So we take the very simple 1D problem, a plane wave exciting an acoustic cavity, and then we have an ending with a poroelastic layer that is absorbing the energy there. And what you see here, you have the response, the mean quadratic pressure in the acoustic cavity. You see the non-damped problem, having the acoustic cavity alone, and then you add a layer of poroelastic material at the end, and you see the damped response, or the damped mean quadratic pressure in the acoustic cavity, with in blue, which would be now the reference response that we are trying to reconstruct using the modal approach. What about those modes? If we calculate them, and then we try to look at what the response looks like if we we increase the number of modes just to get an understanding of a bit of the basis that we are constructing in this way. Well, if we use only one mode, you can have a look here at what the mode looks like, and you may have remember from what Olivier said, is that you can expect to have out-of-phase motions between the solid and the fluid phase, and also, Olivier mentioned, a fluid phase that has a displacement scaled up compared to the magnitude of the displacement for the solid phase. So you know that for modes, the magnitude doesn't mean anything, but the relative scaling between the solid and fluid phase, we calculated coupled modes. That has a meaning in this case. We are projecting on coupled modes. And what do we see here? Well, we see the first mode looks like antiphase, fairly the same scaling of the two phases that we have here. And then for the second one, top, is the solid phase, bottom is the fluid phase. And then you have the scaling, relative scaling between the two, thanks to the scale that we have here. For the second one, you can see that you have a ratio of 1 to 10, about 1 to 10 between the solid and the fluid phase that are actually, for this mode, in phase. And it's very clear that the modes, if we just look at now the compressional modes, which are the ones we are considering now in this simplified problem, 1D problem, they work in pairs. They work one with the out of phase, and then the other one is the different scaling between the solid and fluid phase. And it's only when we have added two of them in the basis to project the whole problem that we have a decent representation of the original full order model in this case. And then we can continue to enrich the basis by adding some modes. A third mode, not major improvements compared to having the first two. And then when we have two pairs of modes put together for the compressional aspects, you start to have a decent response with only 4 modes for this case of the original full order model problem. Now, if we move to, and we will stick to fairly simple example, if we move to a 3D problem where we, instead of exciting with a plane wave, we excite a cavity at the corner of the cavity, we will have later on a 2D equivalent of that one. The problems you see in 2D are similar to the ones you get to see in 3D. It just gets more messy in 3D. So we'll come back to 2D later when we want to have a look at the modes. Here we want to illustrate a bit of the issues that we start to get. You get a corner excitation, and then you get this cavity, you get the cavity modes, then some damping at one of the boundaries at the end. In black here, you have the non-damped response, and then in blue, you have the damped response, full order model that we are aiming for with the addition of the poroelastic layer. What happens if we use this model approach by increasing the number of modes? Well, you see very expectedly, you have a lot of modes that are useless in a way, or very small contribution to the improvement of the quality of the response. So you can see here some kind of a convergence. By the way, we can go for the same criteria. I don't enter into those details, but essentially you need to take a sufficiently large eigenfrequency in order to, so 2 to 3 times the highest frequency of interest, the typical truncation criteria that we have in component mode synthesis or model basis approaches. in order to have a fairly good representation in the frequency range of your interest. I'm not getting into these details. What I would like to highlight here is that there are two things. First, okay, you eventually get to using those kind of modes to an associated problem to the original one. Of course, you have disregarded the middle, the viscous, and the higher frequency stiffness part in order to build the basis. But eventually, you get to a decent representation of the full order model, but you have to include 800 modes in the calculate 800 modes. I don't have the highest frequency of those 800 modes here. I'm sorry about that. But the lesson here is that you need a lot of modes. The other lesson is that within those modes, and it's a little bit expected, given that some are more fluid-driven modes, others are more solid-driven modes, and you have an homogeneous problem, the eigenfrequency problem, you are not really responding to the specifics of this problem, where you have a specific excitation. So between compressional shear modes, the ones that are going to be very impactful in this case, a lot of them are not really contributing, helping the convergence when you actually include them in the basis. So yeah, there are two problems to address. Reduce the number of modes that you would need to calculate. I will not answer that. I think, Ravi, this is something that when you have a very rigid structure and then a very soft structure associated with this, you have these kind of problems where you have a lot of modes that are coming to pollute the basis. I'm not going to look into that. It's a complex question, but it's an interesting one to look into. I'm going to say, okay, let's live with the cost of having to calculate a large basis. Can we extract from that large basis the most significant components that would be helpful for this very specific problem where we have now to account for the kind of excitation that we have plugged into this problem? And this is the question that I will try to answer here now. It's until 3 o'clock. Huh? Yes. So what do we have? Well, the idea is to say that if we just include one of those modes in the model basis, we have a very poor response. But that poor response you get with only one mode gives you a very good residue, right? The residue is a metric that gives you an idea of how accurate your reduced order model is to represent the full order model. Well, perfect. The residue is orthogonal to the model basis, right, that you have built up. So you can use this residue to evaluate how impactful each of the modes that you have at hand is going to help for reducing the initial problem. You can do that by calculating the residue. Residue is calculated, you take this poor response with only one mode for the reduced order model, right? And you just multiply left-hand side, the system global matrix to this solution, minus the right-hand side, and that gives you this residue, which is a fourth kind of quantity in this case. And then you could calculate the displacement kind of quantity associated with this by taking the static problem. If you take the low frequency stiffness matrix for the poroelastic materials, you have a static response there that translates this residue, the force-oriented residue, into a displacement one. And that is useful in order to calculate the quantity that we have here, which is a mass participation of each mode to the specific residue that has been calculated based on one mode. So this is exactly what you have here. What you recognize here, we only take the real part of this force mode here, but what you have here is the displacement residue that you have here, and you're essentially making a projection around the mass matrix to evaluate essentially the contribution of each of the individual modes in terms of mass participation in relation to this displacement-based residue. Here you have a system to invert, and if we note that we use the initial eigenvalue problem that we have, this MP times Kp minus 1 is essentially taking the inverse of the eigenvalues of the initial problem that we have. So you end up having a quantity to calculate that should be an indicator of how good a mode is to reconstruct your response at a very low cost, because you have a very costless solution to calculate, one mode, 1 degree of freedom for the poroelastic material. And these are only scalar manipulations that you have to do here, linear algebra, no inversion. So essentially, when you do this, then you can sort all the modes by the highest contribution, the highest participation factors that you can have. And it looks like this if you do that for the 3D case that I had before. 800 modes I mentioned. This is a log scale. And what you can see here is the log scale of this normalized participation factor, normalized against the smallest contribution of all of them. And you can see that it decays very quickly, which means that you can truncate this model basis further by just keeping the most contributing portions of this model basis. So you can resort the modes, and then you can truncate further the model basis. Then the criteria that you may use to truncate that model basis, this is something that, I mean, there are multiple ways of doing it. This is typically the same thing that we do when we have an SVD and we see that the SVD is decaying very quickly. Where do you stop the truncation? That's problem dependent. You may have whatever criteria to do that. If we do this for the 2D case, so we will go and check. We are back to an acoustic cavity with one of the boundaries having a poroelastic layer. And what we will see now is which modes have been selected as the most contributing, and then where were the position in the frequency spectrum compared to the response. And then for each of those modes selected by these selection procedures, you will see the mode shape with the solid phase on top and the fluid phase on the bottom. And you can see that the first two modes that were, in this case, for the poroelastic layer selected, were actually the first two modes of the initial eigenvalue problem. The most contributing one turned out to be the lowest eigenfrequency ones in this case. But then you start to see that suddenly there is this compressional mode that has actually a big participation to the residue. You remember that they often work in pairs. We find two of them as the third and the fourth most contributing modes in order to rebuild the response. And then a set of other modes that may be difficult to say why they may be more impactful. There may be more analysis to run in order to get that, but one of those could be a link to the type of excitation you have in your problem. What happens if we have a look now, this selection, how does it work when we use this 2D case, which, by the way, would converge after 26 modes for the poroelastic layer in the selection. So you reduce initially 150 degrees of freedom for the poroelastic layer. You can reduce them to 26 degrees modal coordinates for the poroelastic layer. And you could see the same issue as we pointed to in the 3D case, is that the convergence is actually not really sorted as we usually see in poroelastic in modal methods, where the low frequency converge very quickly. But on top of that, yeah, you can see the same issue that some of the modes are not really contributing. Now, if we apply this selection and resorting approach, what we can see is after 4 modes now, we have a convergence up to about 50% of the range of frequency that we are interested in this case, and that after 8 modes instead of 26 only, 8 modes are then sufficient as the main contributions to have a decent reconstruction of the full order model, to which with we started the discussion. The 3D case, you remember 800 modes eventually to get the full approximation. If we apply the same procedure, this is after 2 modes of selection, we already have the first peak that is well captured here. And then if you, after 58 modes selected, the first most significant 58 modes, you have convergence to about the 50% of the range. And then with 80, more or less 80 modes instead of the 3,000 initial poroelastic degrees of freedom, you have a decent representation of the initial problem. You remember this question that we use the modes based on this low frequency stiffness and this mass matrix alone. There's no guarantee that this will lead. There's no orthogonality property that is a priori known for the middle matrices there. And that we can just have a check. Looking at the projection of those middle matrices on this model basis, what is the sparsity? Do you have a diagonal or piecewise diagonal or sparsely populated or fully populated middle matrices? Well, this is the kind of sparsity analysis that we can do. You have the acoustic degrees of freedom here, the sparsity, and this all the degrees of freedom associated with the poroelastic layer. Then you project the initial projection of on the model basis, and what you get to see is that, okay, the coupling between this at the interface degrees of freedom, this is fully populated. This is due to the component mode synthesis approach. This is not what we are looking at. What we're interested in here is this part. And this part tells you that about 50% of the matrix is indeed diagonal, and the rest is fairly sparsely populated, which it's a bit, there's no proof in there. You're just checking a posteriori, but essentially it tells you that the subspace spanned by those two, the eigenvalue problem based on this low frequency stiffness matrix and mass matrix, may be decently aligned with those the one that would have been generated if we would have taken the other matrices that we have in the initial problem that we have neglected for the eigenvalue problem. If you select, this is here the sparsity that is represented. When you select for the 3D case here, 3,000 degrees of freedom, you boil it down to some 80 degrees of freedom at the end. These are the remaining poroelastic degrees of freedom in your whole problem that you had from the start. And this matrix that you have here is the one that is represented here in terms of sparsity. So it's indeed a very sparsely populated poroelastic matrix. Last bit. With modal methods, and complex dynamics, as in the poroelastic materials, where you have a fairly rigid part of the problem, and then you have the fluid part where many modes can also come from that without a big contribution to the overall response. If you go for the homogeneous problem without directing the efforts toward the actual excitation that you're putting on it and discarding some of the components from the get-go, you end up having this large initial basis to work with. That's not optimal. So then in those cases, there are a range of many methods actually, which actually include knowledge from the kind of excitation that you have. And Padé-approximants are directly trying to expand the solution, the specific solution that you are looking at, from a frequency point in the spectrum that you are interested in, is one of the techniques here that we are going to look at the local rational expansions from a specific point, which has derivations in the projection-based methods, which you will see in the second part of the set of lectures. Here we will talk about Padé-approximants because they are nice ground to move on to the arguably better methods in terms of reduced order models for the sake of reducing, but there are some interesting features about those. Essentially, what we got to see up to now is this type of problem to solve, right? And then regardless of the type of the system matrix that you have, if we have a poroacoustic problems, it may have this form with a complex frequency dependency, and we managed, or we showed here that we could write it in terms of combination of frequency-independent global matrices that are then recombined by a range of functions more or less complex in terms of frequency dependency. And the idea here is to say that let's look at the response and then expand the response from a set frequency instead of trying to project without specifically looking at the specific force response problem that we have at hand. And one idea, naive idea, is to use Taylor expansion series, but as you know, we have solutions with many poles, and Taylor series are bounded by the poles that you have in the response, which makes them non-suitable to actually the type of problem that we are interested in. But they are still at the basis of what we are looking at in terms of Padé-approximants, because Padé-approximants are essentially expansions in terms of Taylor series in the form of rational functions. So you have here the Taylor coefficients, which, by the way, is important, are based on their calculation of the successive derivatives at a specific point of interest of the solution that we have here. Padé-approximants are looking at just rational expansions or rational functions of those expansions in terms of numerator and denominator. The question is, how do those coefficients pk and qk, so the numerator and denominator expansion series, how are they evaluated? Well, one way is that they can be equated, those rational functions, to the Taylor expansion series. So you have here the Taylor coefficients or the expansions, and then the Padé-approximants or the rational expansions. And from this, you can equate those in order to establish a linear system of equations. How does this linear system of equations works? Well, from this, you have two steps. A first step, which in red, you will have all the known, okay, those are possible to calculate Taylor coefficients, which you can get from successive derivatives of the solution. And those can be set into a linear system of equation in a matrix of this form. Note here that you have all the higher order from L to, all the higher order coefficient that you need to calculate in order to set a linear system of equations, which will give you in solution the coefficients associated with the denominator, so associated with the pole. That's the first steps. And if you continue to look at this linear system that is established there, the numerator coefficients that are there, they are just obtained then by manipulation, multiplication between those denominator coefficients and the Taylor coefficients that we have here. Okay, so this is the costly step in this aspect. To evaluate the coefficients, you need to calculate the Taylor coefficients, and you need to solve very small linear systems of equations in order to get the poles that you have here. How are those calculated? Well, we said we need the successive derivative of the solution at a given frequency. Well, it turns out that this is done by a recursive approach, where you have here a fixed system matrix at the frequency of interest around which you are going to expand the solution. And you can calculate the successive derivative by involving then lower order terms of the solution that you have had before, and the right-hand side of the problem, the initial problem that you had here, the specifics of your problem, the forced response that you have from the beginning. I will pass the details in order to get this, but essentially the procedure, it goes like this. You set a frequency around which you want to expand the solution. You calculate the global matrix, system matrix at this frequency. You perform a matrix decomposition. You solve for the solution at this point, and then iteratively you calculate the successive derivatives with a recursive approach that we presented in a previous slide. Then you have a very small, for each degree of freedom of interest only in a solution vector, you have a very small linear system of equation to solve in order to get to the denominator expansion coefficients. After that, the second step is you have multiplications to get to the numerator coefficients of the series expansion. And finally, you just have an evaluation of the response by evaluating the expansion that you have established at different frequencies around the frequency of expansion. There's a question of what happens now. You will expand your solution around the one specific frequencies. Well, we have broad frequency ranges, so you need to choose expansions around multiple frequencies. This is a question of sampling, of how do you determine those frequencies around which? Maybe Stefan will be talking about that the second part, I don't know, but there are multiple techniques existing in literature. This is not something that I will detail in this case. I just want to highlight to you the comparison for this 1D problem that we had at the beginning, a comparison between an expansion around a fixed frequency that you have here. You remember in blue is the reference solution. If you try to expand that using Taylor series expansion, you will be very quickly blocked by the first poles that you find in the solution. And if you use Padé expansions, by increasing the order or the number of derivatives you include in your reconstruction, you can see that you can expand the solution fairly decently in the frequency range. This is after using 11 derivatives in this case. Now, why did I include the Padé? I think there's an interesting point to be made with the modal methods. You remember, we tried to expand the solution in terms of expansion of zeros, essentially having a polynomial there with zeros, and then the zeros of the denominator, which are the pole of the solution. Now, the poles of the solution, what are they? What do they correspond to? And remember that the poles, those poles, in the Padé method, they are the ones who require the highest Taylor coefficients. And the highest Taylor coefficients means the higher order of derivatives. If we have an alternative way of getting those poles, we will save ourselves some troubles in terms of calculating successive derivatives. And it's not only interesting in terms of computational aspects, is that what I didn't mention here is that the successive derivatives collapse in terms of accuracy in these recursive schemes. So if you can stick to having a reduced number of those successive derivatives, you are at an advantage if you try to use those kind of methods. Well, the poles of this solution that we are looking at, they are linked to the homogeneous problem that we have from the start, right? The eigenvalue problem that we are trying to solve. Those correspond to the poles of the solution, which means that if we happen, and we will illustrate that for the conservative when you have non-damped problem, but if we happen to have the modal basis, well, we can use the eigenfrequencies that we have from the start in order to evaluate the poles that we need for the denominator polynomials. So let's illustrate that. We said, this is what I mentioned, right? The first step was to solve a small linear system in order to get to the denominator coefficients of the polynomial expansions there. And this is where you notice that you need to calculate the Taylor coefficients of the highest orders in this. So the right-hand side that you have here imposes that you go to try to get the derivatives at the really high order. Let's try to skip that step, using the fact that the roots that the roots of the problem here of the left-hand side, the system matrix, are a way to get access to directly those poles. So if we are given the eigenfrequencies of the problems of interest to get started with, well, the denominator zeros, or the poles of our problem, can be directly equated from those two terms, those two sides of the equality there. So let's say that from the eigenvalues, then we determine this Q1 to Qm. We can use just the second step that is unchanged. The second step is just multiplication of those poles with some of the Taylor coefficients that we had before, and we can reconstruct the numerator coefficients that we needed for the expansion. Another thing that is really nice is that for Padé-approximants, the convergence, there is a theorem that states that the range of convergence that you can hope with a rational function to reach is actually determined by the number of poles that you capture within this range. Which means that in terms of convergence, what you can use the poles in order to set the range that you can at best reach for approximating the rational function or the solution in our case. And then the convergence is driven by the numerator coefficients. Then you just have a Taylor series to expand. It's the order of the numerator that is going to dictate how well you converge to the best possible converged solution you can have dictated by the poles. Very nice, because the poles in our case, we said we equated them to eigenfrequencies. If we have the eigenfrequencies, we choose a set of those eigenfrequencies that tell us if you choose a certain number of eigenfrequencies, well, all the eigenfrequencies that are included define the range that you can at best reach for a converged solution. And then you have an expansion of the numerator that tells you how well you will be converged in this range that you have. So the procedure goes like this. Let's assume that we have the poles, we have the eigenfrequencies, we can determine then the denominator coefficients of the series expansion. Then we still have to solve for a set of Taylor coefficients, but much lower, fewer of them in this case, just associated with the numerator order of the expansion. And then we can rebuild that thanks to the eigenfrequency, and that thanks to the Taylor coefficients. Let's go back to a 3D cavity, simple problem to illustrate. We have an acoustic cavity that is going to be excited at the corner. And I'm just comparing here the case where, and this is the last example, so then you will have your coffee break without it being stolen away completely from you. But what you have here, we are going to try to expand in red here the reference solution, conservative, so you have those peaks appearing all around. And what you have in M is a number of denominator coefficients that you have taken. So it's the order of expansion of the denominator. And L is the order of expansion of the numerator. M is equal to 4, which means that we have included 4 eigenfrequencies for the expansion of the rational function of our interest. The 4 eigenfrequencies that have been included are the 4s that we have here in red. So we know that at best with this rational function based on 4, an order of 4 for the denominator Taylor series, we can reach a convergence between 133 Hertz, 1333 Hertz, and 1786 Hertz. So essentially, we cannot hope, or we cannot, of course, you could if there's no pole beyond that, but we know that for the poles between those, we can aim for a converged solution. And then in this case, I took a high order, in this case, of numerator coefficients for the sake of checking at the convergence in the best configuration case. And on the left, what you have here is the method where you calculate Padé based on, in this case, it would be more than 18 derivatives, 14 plus 4. In this case, you have only 14 derivatives. That's the convergence of the numerator, only the expansion of the numerator. What we get to see is essentially fine. We have good convergence in the middle, but you can start to see at the boundaries where that's where it's most interesting in this case that should be converged, is that here you fully captured what you actually know that you should capture, 1786 Hertz, where here it's not completely the case. You don't really control that. It may be associated with the loss of accuracy when you are going to the higher orders in terms of the successive derivatives. And we could move this forward. I could go to the last case. In this case, we know that we include 12 eigenfrequencies. Essentially, all the eigenfrequencies that we have in the range that we are considering here, between 500 Hertz to 2000, over 2000 Hertz. And we know that this is what we can reach in terms of convergence. And here, I didn't go for a numerator order of 12 plus 10, 22, for instance, because for this case, you increase the numerator order, you don't see any improvement in the convergence of the solution because you are going so high in the number of derivatives that you need to have that you have lost the degree of accuracy that you need in order to rebuild the solution. So in this case here, for this case, there we would have to calculate already some 28, 29 derivatives of the initial problem. On the right side here, you only have to calculate 16. And what you can see, obviously, is at the boundaries, how you gain here in this case, is that you're actually capturing exactly at least everywhere where you have the poles or where you have the peaks of resonance when you cannot in the initial case. And I will conclude on this. I will just say that what we don't say here, that this loss of accuracy with the successive derivatives is a strong limitation. The nice thing here is that you have a piecewise analytical expression for the solution, and you can also handpick a few degrees of freedom. So if you have a response needed only at one point, it's very efficient to go for a method like that. But then there is since you calculate a very nice approach, you have all the derivatives. You have the derivative for all the degrees of freedom in your problem at multiple orders. Well, those could constitute a basis on which you can project the whole problem. And if you use that as is, this is not a good basis because it leads to ill conditioning for the same reason that you are losing accuracy with the higher orders of differentiation. But this is at the basis of a lot of the other methods that you will be maybe hearing about, the moment matching methods, the Krylov-based, Krylov subspace. You have all those methods that come and actually have many links to this kind of approximation. I will stop here, but I hope that you can continue and elaborate on this when you come between modal methods or frequency sweeps in the second part. Thank you. I hope that you could get something from there. Welcome with your questions.